This is Algebra 2 with Trig 7A.3. We're talking about explicit sequences, specifically the geometric format. So here's an example of a sequence, or we're going to create a sequence of numbers that's being created by multiplying by 2 every time. So a of 1 equals 3 times 2. 1 minus 1, when you plug a 1 in for n, you get 1 minus 1, which we all know is 3 times 2 to the 0 power. And anything to the 0 power is 1. So that's going to give us an answer of 3. 3 times 2 to the second power minus 1 is really 3 times 2 to the first power, which is 2 times 3, which is 6. And you can keep going with that same pattern. 2 to the 3 minus 1, which would be 2. So that's 4 times 3, which is 12. And 3 times 4 minus 1, which is 2 to the third power, which is 8 times 3. And our fifth one is 3 times 2 to the fourth power, because it would be 5 minus 1. 5 minus 1. That's 16 times 3, which is 48. If we graph that, look what happens. At 1, we're up at 3. At 2, we're up at 6. At 3, we're up at 12. And at 4, we're up at 24. That would be up here. Very good. It's not linear, especially when the next point is way over here. That's definitely not on that line. So it's not linear. We're exponential because we are repeating the number 2 multiple times. We have a translation if you think back to our exponential graphing days. So this is an exponential family. The pattern is multiplying by 2. That's what's happening with this formula of a sequence. So the explicit rule, whenever we write a rule for a geometric sequence, if we know the first term, this time we put the first term into our equation. Because of the way the formula is written, n minus 1 allows the first term to be there, times r to the n minus 1. You have to have n minus 1 there. If you didn't have the n minus 1, then the a value would not be the first term. So we're going to write a rule for the nth term of a geometric sequence with the first term of 5 and a common ratio of 4. So we write our formula as 5 times 4 to the n minus 1. You cannot call that 20 to the n minus 1. Okay, what we've done in the past. What's the difference between y equals a times b to the x and our explicit form of a of n, a of 1, times r to the n minus 1. These are two equations that are creating an exponential graph, exponential list of numbers. In this case, this is not the first term. This would be your y-intercept. In this case, this is your first term because it's been translated to the right once. A of 1 is not the y-intercept. That's what A was. A was the y-intercept. A of 1 is not the y-intercept. That's the big difference between those two. We've been translated one to the right. If you look over here, we typically would start at 1. Every exponential is going to go through 1 unless it has an a value. The a value is 3. So we're going to times the 1 by 3. That takes us up to the 3. Then we translate it 1 to the right, and we land right on that spot. This graph has been translated once to the right. And we know that from our H and K rules. So we'll come down here and we'll talk about writing a rule for this sequence, this list of numbers. What pattern do you see? Well, the numbers themselves look a little tricky. Remember, we are in a geometric unit, at least a section. And I can tell very quickly that it is not going down by the same amount. It's not arithmetic. So we are going to have a geometric test of a term divided by the one before it. So that's going to be 2 divided by the one before it, and that becomes 0.4. If we try it again, because you know you have to try it more than once, half of 0.8, of course, is 0.4, so that makes sense. And you can even do it here. 0.8 times what would make 0.32, or how many times does 0.8 go into 0.32? It goes in there 0.4 times. If you multiply, you would get 0.32. So anyway, these are all 0.32. So the R value is, or they're all 0.4. So we know our first term is 5, and our ratio is 0.4. Those are the things you need to know to write your equation. So A of n is going to be 5 times 0.4 to the n minus 1. And you can test this. You can take your 5 to the 0.4 to the 1, 2, 3. Let's do the third one. 3 minus 1, and we should get the answer of 0.8. So we tested our formula to be sure it was accurate. So we need to have A of 1. We need to have R. In this case, we had to figure out what R was. It wasn't too tough. Term divided by the one before it gave us the R value. Now, what if you don't know both A of 1 and R? Then we're going to do some substituting. We did this earlier this year when we were talking about equations. One term of a geometric sequence is A of 4 equals 12. So we don't know A of 1. we need to know A of 1, and we need to know the R. If we know those two parts, then we can write our equation. Well, here we know that the R is 2. So that's simple. But we don't know what A of 1 is. If we use our formula, A of n equals A of 1 times R n minus 1, similarly like we did yesterday, we're going to plug in our 12. We don't know A of 1. Our R value is 2. Our n value is 4, then minus 1. So this is 12 equals A of 1, 2 cubed. So 2 cubed is 8. So when we divide, we get 3 halves equals A of 1. 4 goes into 12 3 times, 4 goes into 8 2 times, so that reduces to 3 halves. So there's our answer to the A of 1. So we're ready to write our formula of A of 1 times R to the n minus 1. So where I got my 4 and the 12 was the coordinate that they gave us. They gave us 4, 12. Just like we graphed earlier, up here, A1 was at 3, A2 is a point at 6. So this is just a point at 4, 12, and I plug it in for my A of n and my n value. I didn't calculate A of 8. A of 8 is going to be plugging in an 8 for n. So we have 5 times 0.4, 8 minus 1. So A of 8 is going to be 5 times 4 to the 7th power. 5 times 0.4 to the 7th power is a crazy decimal. You wouldn't want to round this to the nearest tenth, because that would be 0. We know that's not the truth. We don't want to round it to the nearest hundredth. You could get away with 0.01, I guess. But this is just more accurate. It didn't go on forever, so I wrote down all the numbers. All right, now hold yourself together on this one. No crying in mathematics. You can do this. If we don't know R and we're given 2 terms, okay, we don't know R, we're given 2 terms, but we're not given A of 1 either. We're going to have to calculate both the R and the A of 1. We've done this before with X's and Y's. Same exact thing. So here are 2 points. So we have 3, negative 48, and we have 6, 3072. This gets a little intimidating, but you can do it. We need to know, we are looking for A of 1, and we're looking for R. That's what we need to know. To write our equation of a geometric, we need to know those 2 parts. Okay, slope doesn't help us here. That would be our explicit formula for an arithmetic. But this is supposed to be geometric. So we have to use our geometric rule, which is A of n equals A of 1 r n minus 1. So we're going to plug in negative 48. I don't know a of 1. I don't know r. My n is 3. Then I minus 1. So this is negative 48 equals a of 1 times r squared, because 3 minus 1 is 2. Now here we like to divide and get the a of 1 by itself. Now we know what a of 1 is, but this is a of 1 in terms of r. We can't put that a of 1 here. We can't put negative 48 over r squared. So we still need to figure out what the other part is. So we're going to come over and use the other point. We're going to take our 3072. We have this value that is a of 1, negative 48 over r squared, times r to the 6 minus 1. That's 3072 equals negative 48 r squared times r to the 5th. Algebraically, how can I reduce that? You all know how to do this. What you have to decide is, how do you simplify this? The 5th root of both sides would be getting the r by itself. We're not necessarily at this given second trying to get r by itself because we have two different r's. But we are going to subtract our exponents because we have a fraction. All right, they're both considered on top. R squared is on bottom. So we have negative 48. How many more r's do we have on top than we have on bottom? We have 3 extra on top than we have on bottom. Because 5 minus 2 is 3. We would have to divide by negative 48. That gives us r cubed equals negative 64. Now we can take the cubed root of negative 64 and the cubed root of r cubed, and that gives you negative 4 equals r. We did it. So r is negative 4. But what don't we know? We don't know a of 1. So we take negative 48 over negative 4 squared, because a of 1 is negative 48 divided by r squared. That's negative 48 over, now be careful here if you're not thinking about it, many mistakes happen. This is actually positive 16. So now we're able to write our equation. A of 1 is negative 3, our r is negative 4, n minus 1. That is pretty intimidating there, but you can do it. Think about what we did. We were given 2 points. So we plugged in our 3 and our negative 48 for the first point, and we narrowed down. We plugged it into the second point, so we had one variable by itself. Then we were able to plug that in to figure out the other variable. So in 1990, the total box office revenue in the United States movie theaters was about $45 billion. Thanks to you guys for going to the movies more than one time. In 1990 through 2003, the total box revenue increased by 5.8% per year. What family of functions best models a situation when a quantity increases or decreases by a percentage? exponential. Yesterday we had, what was a family of model that, or what is the family that best models a situation of a quantity increasing or decreasing by the same amount? This is by a percentage. So that's where the differences lie from yesterday's lesson to today's lesson. This is exponential because we're multiplying, we're doing it by a percentage, where yesterday we were increasing by the same amount every time. Write an explicit rule for the total box office revenue in billions for, or assuming that n is 1, and that represents our 1990. So, if A of 1 is 1990, and A of 1 was 45 billion, and we're increasing. So what is our rate going to be?
5.8%.
It's 5.8%. So do I write 5.8? 0.058 is what this would represent. But if I try to calculate what 0.5% is, 45 billion times 0.058, that's going to give me 2 billion. That means we went down. We were at 45 billion, but now we're at 2 billion. I thought we were increasing. What happened? We could add this amount to that amount. What's going on? Okay, we're going to start over. 45.02 times our 0.058, that gives us that amount. And when we add it to 45.02, we get that amount. This is what we want. How can we come straight to this amount? We want to put 5.058 on top of 100% of this. So we need to take our 45.02 and times it by 1.058. 100% and 0.058. There we have it all calculated in one amount. So we need the 1.058. We want 100% plus our interest rate, or how much it's increasing by. 1.058. So our A of n equals 45.02 times 1.058 n minus 1. What would be the recursive rule for this? You know your recursive rule needs a couple things. What do we start with the recursive rule? The first term. 45.02. You need to know where you're starting. Then what is the recursive rule going to be? We're going to take the previous term and times it by our interest, or by our amount that is changing by. So I would put that number first times A of n minus 1. So you take the previous term times this amount. Our previous answer was right there. Okay, so that's what we're trying to get. So if we take 45.02 and we times the answer to 1.058, that is taking the previous answer. That's a recursive idea, rather than 45.02 times 1.058 to the power of 2 minus 1. There's our 47.63. So this is explicit, and this is the recursive. They give us the same answer, but it's two different ways that we format it. What is A of 5? Well, how are we going to figure out A of 5? A of 5 is going to be, so I don't have to write it again, A of 5 is going to be 45.02 billion times 1.058 to the 5 minus 1 power. So 45.02 times 1.058 to the power of 5 minus 1, which is 56 billion. 56.41 billion. What does this represent? Well, this is where it gets a little confusing. If 1 represented 1990, n equals 1 represented 1990, n equals 2 represents 1991, n equals 3 represents 1992, n equals 4 represents 1993, and n equals 5 represents 1994. So what does A of 5 represent? It represents 1994. 5.6 or 56 billion, and this is the amount of revenue in 1994. Okay, this is when I graduated high school. So it's so much money because of how many Batman shows I went to see. Okay, what type of rule, explicit or recursive, was more efficient? Well, I often say the explicit rule is more efficient because we only make one calculation. We did one calculation. We plugged in the 5 and we did our one calculation. If you were going to use the recursive, you would figure out your starting point. You would times that by 0.0 or 1.058. So that would be 2, 3, 4, and 5. We get the same answer, but you would have to do the multiple calculations. It's not very hard in this case because we only had to do 5. But if we had to do 60 like we did yesterday, recursive is out of the question.